Welcome to the 8th lecture from chapter number 7. We are studying VLSI design, and in this lecture we'll study about propagation delay. In last lectures we have been studying about rise and fall time delays, and we derived expressions for TR and TF, the rise time and the fall time delays. In this lecture we will study about the propagation delay, TP, and we see that TP is the total reaction time from input, or total reaction delay, or reaction time, or the total delay offered by a logic circuit from input to output, and it is the average of the fall time delay and the rise time delay, because it's an average value, right? So TPF is a bit different from TF. We have been studying about TF without the small p. Now we are studying TPF, propagation fall. TF was the delay in which the output falls from 90% to 10% of VDD. You remember that. And TPF is the delay where the output falls from VDD, instead of 90%, falls from VDD to 50% of VDD. This is TPF. So the definition is a bit different from TF. TPF, the definition is a bit different from TF. TPF is the time in which the output falls from VDD to 50% of VDD. Similarly, TPR, the definition is a bit different from the definition of TR we studied previously. TPR is the time in which the output rises from 0 to 50% of VDD. In contrast, TR is the time in which the output rises from 10% to 90% of VDD. So it's a bit different from TR. This is TPR, in which the output rises from 0 to 50% of VDD. So right, with these definitions in mind, we can straight away compute TPF, TPR, and TP for a CMOS NOT. Right, so that we have been studying. Right, what is TPF for a CMOS NOT, where we know that this equation is this graph, or this plot is governed by this equation, VDD to the minus T over tau n, where tau n is Rn C out. You know that, right? So when we were studying about TR and TF, we actually rearranged these terms to bring T on the left hand side and everything else on the right hand side, and here we'll do that once again. Right, so that practice is to divide this VDD here, and then we can compute log on both sides, so it becomes log of VFT over VDD, and this is left as minus T over tau n, or we can write T as minus tau n log of V of T over VDD. So this is how we can write T for this curve, the falling curve. All right, and we know that that this TPF is the difference between the times. Let's label these times. Let's call it dy, let's call it dx. So TPF is the difference of time between dy minus dx, right? Dy is the time at which the output is 50% of VDD. V of t is 50% of VDD, or 0.5 VDD. So this, in this equation, we will replace V of t with 50% of VDD. So this is minus tau n log of 0.5 VDD over VDD minus dx, which is minus tau n log of, it's the time at which it is 0, the output is 0, so 0, V of t is 0, 0 over VDD, 0 over VDD is a 0, so 0 and log of 0. is not defined. So therefore it's not VDD, it's VDD, it's not 0, it's VDD, right? So this is minus tau n log of VDD over VDD. I see, it's not 0, it's VDD. So VDD over VDD is a 1 and log of 1 is a 0, that's right. So TPF is the time for which it has risen from, it has fallen from VDD to 0.5 of VDD. So this is minus tau n log of 0.5 minus this whole stuff is 0 because log of 1 is a 0. So this is minus tau n log of 0.5. So TPF is minus tau n and log of 0.5 is some minus 0.69, minus 0.693. So TPF is 0.693 times tau n. This is how we can compute TPF, right? On the same lines we can find TPR, right? So TPR can be computed. So keeping this as a separate result, TPF is 0.693 times tau n. We'll use that later, and now we can remove everything else on the board. Right, with this useful result we can remove all these calculations. Right, so now we can start working with this TPR, which is equal to TPR, and we know that this, for this curve, the equation that governs this is VDD times 1 minus e to the minus t over tau p, where tau p is RPC out, we already know that. And this equation we studied in linear circuit analysis, LCA, in first semester. Right, and we have to rearrange terms so that we have t, small t on the left hand side and everything else on the right hand side. So we can write it as e to the minus t over tau p, taking this on the left hand side, taking this on the right hand side, 1 minus v of t over VDD. And then taking log on both sides, this becomes minus t over tau p. Right, and t can be written as minus tau p log of 1 minus v of t over VDD. So this is the equation that we'll use to compute TPR. So let's compute TPR. It's the difference between this ty and tx. At ty we have 0.5 VDD, v of t is equal to 0.5 VDD. At tx we have v of t is equal to 0, right? So ty, this is equal to ty minus tx. This is minus tau p log of 1 minus v of t is 0.5 VDD at ty, 0.5 VDD over VDD. minus dx, which is, it is 0. So v of t, put v of t is equal to 0. Minus into minus tau p plus tau p log of 1 minus, this is 0 over v dt. Right, so log of 1 minus 0 is log of 1, and log of 1 is a 0, so this whole terms becomes 0. So now it is, now TPR can be written as minus tau p log of, this VDD cancels with this is in 1 minus 0.5 is 0.5, log of 0.5, and this is minus tau p log of 0.5, log of 0.5 is 0.693, but negative minus 0.693. So TPR is 0.693 times tau p. TPR 0.693 times tau p. So with this small calculation, we have computed, or we have derived expressions for TPF and TPR, and now we are ready to compute the propagation delay TP. And we know TP is TPR plus TPF over 2. 0.693 taken as common, tau p, tau n over 2. So this is approximately 0.35 times tau p plus tau n. It's an expression for the propagation delay. Right, so that's all for this lecture. In the next lecture, we'll study another important concept, area speed versus area trade-off. Thank you.